Drunk driving is a major cause of accidents in Virginia localities. Just last year, a staggering 27% of all traffic fatalities in Virginia were alcohol-related, and 14,247 people in total were convicted of a DUI. Various studies have supported that socioeconomic factors such as education level, income level, and unemployment play a key role in drunk driving occurrence. Our goal is to train a classification model to predict the incidence of a drunk driving accident from traffic accident and poverty data. This model will help notify which counties should be on the highest alert for potential drunk driving accidents, keeping roadways safer and emergency vehicles prepared to handle these situations.
2 datasets were then used to train our model: a poverty dataset for counties obtained from the Virginia Open Data Portal and a National Highway Traffic Safety Administration dataset containing traffic accident metadata in Virginia. The datasets were then merged in 2 steps. First, we found county IDs both datasets had in common and filtered them separately to remove any samples that neither had in common. We then wrote a function that, given a year between 2015 and 2018, which were the years that overlapped for both datasets, it would return a merged dataset of the poverty and accident data for that year. Once the dataset was merged, we generated graphs for features we were interested in examining. Graphs 1 and 2 show that most drunk driving accidents occurred in September and March, and were most likely to occur during the weekends. Graphs 3 and 4 show that drunk driving accidents were also more prone to happen at night in dark, unlit conditions. In Graph 5, we identified the top 25 counties with drunk driving accidents, the top 5 being Fairfax, Newport News, Prince William County, Chesapeake, and Richmond City. Lastly, Graph 6 displays the poorest counties, which are Greene, Goochland, Madison, Richmond County, and New Kent. None of these counties overlap with the most drunk driving accidents, leading us to believe that the correlation between poverty and drunk driving accidents may not be that strong.
Initially, we performed k-means clustering on the dataset to determine whether clear clusters would form when relating poverty level to the number of drunk drivers in an accident. The results of this were suboptimal. No clear clusters formed. This was likely due to the high number of categorical data present and how the majority of crashes had only 1 or 2 drunk drivers.
These results supported that binary classification of accident type would be a better option. We tested 3 models for this purpose: support vector machine, random forest, and a custom neural network architecture.
At first, a large majority of the dataset consisted of crashes that had either 0 or 1 drunk drivers, with a few instances of 2, 3, and 4 drunk drivers involved. Since there was not much data that involved more than 1 drunk driver, we decided to train a binary classifier where the label was 1 for the incidence of a drunk driver involved in the crash and 0 for no drunk drivers involved. The dataset was then split into 3 subsets: training, which was 70%, validation, which was 10%, and the test set, which was 20% of the original data frame. Lastly, we used one high encoding for categorical variables and a mean imputer strategy for missing numerical values in the pipeline.
We tested 3 different SVM kernels: linear, polynomial, and Gaussian, and conducted grid search to optimize hyperparameters. Results were similar for linear and polynomial kernels. However, Gaussian performed quite poorly with 60% accuracy and 0% for both precision and recall. So far, our best model is the polynomial SVM with an accuracy of 82%, precision of 89%, and recall of 48%. Next, we used a random forest classifier, optimizing hyperparameters with the grid search. These results were comparable to the linear SVM, with a precision of 80%, recall of 48%, and an accuracy of 80%.
Our final test was implementing a custom neural network architecture via Keras. The architecture consisted of an input layer, 4 layers of alternating dense and dropout, a dense layer with ReLU activation, and a final dense layer with a softmax output of 2. The multiple dropout layers were used to aid our problem with our model severely overfitting the training data. After constructing the neural network, we then trained it for 50 epochs. The test set accuracy of 0.78 was worse than the FCM model, and the validation loss further increased with each epoch, indicating that the model was still overfitting the training data despite the numerous dropout layers. Even after lowering the number of epochs, the accuracy was still lower than the SVM model, so we decided to use the SVM model as our final.
The best model performance had an accuracy of 82% and precision of 89%, but a recall score of only 55%. We attempted to increase recall scores by optimizing recall, adding more data, or deleting features with low correlation, but found that these methods decreased precision and accuracy scores more than improving recall scores. To summarize, our polynomial SVM model outperformed random forest and neural network approaches to predict the incidence of a drunk driving accident, but there is still room for improvement. By implementing this model, we can prepare first responders and increase alertness of other drivers to create a safer road environment.